Hello class, welcome to another video for this course. In this video we are going to study section 4.3, the definite integral. So we talked about Riemann sum, and we saw the effect of the number of rectangles, the number of subdivisions on the area under the curve. So here we want to precisely study the effect that increasing the number of subintervals have on our approximation generated by Riemann sum. And also after that we want to define the integral of a function over a closed interval, and then what does this exactly mean, and how can we compute it? Okay, so let's look at this figure. In this figure you can see you see three figures, but all of them are about the same thing. We have the curve. The blue curve is the function, the graph of function f of x, and then we are looking at the area under the curve from A to D, I guess. Yes, here A to D. And then as you can see in the figure on the left side, we have we used some rectangles. So we put some rectangle because we know how to calculate the area of rectangle. So instead of calculating the exact value of the area, we use these rectangles in order to estimate the area. Look at the figure in the middle one now. The figure in the middle one has more rectangle. In other words, it's like we divided the interval A to D into more sub-intervals. So now we have more rectangles and each one is more narrower, right? And in fact, this yields to a better approximation. Why? Because now we have less error, and all of them are so either the figure on the left or the figure in the middle one, they all are for estimating the area that is that is highlighted in the figure on the right side, which we denoted by A1, A2, A3. So in this picture, A1 has the color of, I don't know, blue or purple, and A2, I don't know, pink, some orange, something like that. And the reason for different coloring is that A1 and A2 shows a region that is above x-axis, and A2 denote a region that is under the x-axis. So in terms of area, because recall that the meaning of area is positive. So in that sense, being above x-axis and below x-axis make a difference. So if you have a region that is above x-axis, in the computation of area, that comes as a positive number. But if you have a region that is under the x-axis, that would be a negative value in the computation of the area. Okay, in last video we looked at this applet, but because this is very cool, let's look at this activity, this preview activity, and which use this applet again. So I encourage you guys to play with this applet. In this applet, you can insert any function in this box. In this box, you can put the equation of the function. It gives you the curve, and then you can use let me go to it, and then you can do whatever you want. You want to do a Riemann sum, you want to do approximation, you can do that, and you can change the setting, for example. So this is the default of the function. Let's look at the activity. So in this picture, what you see is the right Riemann sum with 10 sub-intervals of this function f on the interval of 1 to 7, and the value of this sum is 4.90, which is also here as well, you see. But you can change it if you want. And I think in this activity it asks you um, to play with it. So if you need to refresh your mind of what is what, here it describes that exactly each feature. So for example here, it depends on what you want to do. You want to do a left, you want to get a left Riemann sum, so you can put the slider on left endpoint. You want to do a right, you put right endpoint. You want to do a midpoint, you put it on midpoint. And if you want to do any arbitrary random number, you can just click random, and then on each within each subinterval or within each rectangle, it pick the software pick a random value to do the calculation. And then it calculates the approximation for you. The relative approximation is the area, that's the area under the area of these boxes, the area of these rectangles, which we use them in order to approximate the value, the area under the curve. Okay. And I think in your textbook, it asks you to now try to do, it says, do a left Riemann sum. Okay, left Riemann sum, left, with a 5 sub interval. Okay, so now we want to have 5 sub interval. The default is 10, so let's change it to 5, which means now that we have 5 sub intervals, so that means we have 5 rectangles. So we need to calculate. You can also, 5 is a small, you can also do it by hand, but that means we calculate the area of 5 rectangles. And then the function is 2x plus 1. So I'm going to change the function as 2x plus 1. Okay, that's going to be a line. Um, so the function is 2x plus 1. So that's the function. Let me see if I can zoom this. Yeah. So you can see, and I want 5. So this the setup is 5, not 7, 5. The setup is 5 subintervals or 5 rectangles, and it says end left endpoint. So this is gonna be the big picture. Okay, so we have so the textbook said this activity says that now try this, try to adjust the applet as a left Riemann sum with 5 subinterval for 2x plus 1. Now you should see this figure. Yes, we are seeing this figure. So now what is the left Riemann sum? Oh, I didn't change the interval. Okay, so I need to change it from where to where? The textbook says between 1 to 4. Okay, so update the applet so that the function begin being considered as this on 1 to 4. Okay, so I need to change the interval to, okay, because the default is something else. So it's gonna be 1, the default is 1 to 7. I need to change this to 1 to 4. Okay, there we go. There we go. So now we have the equation, the graph. The graph is, look, if you just want to see the graph, just do this. So this is the graph of 2x plus 1. It's a line. Now, we want to do a Riemann sum. And the question says, do a left Riemann sum. So I put this slider as left. So that means it for the height of each rectangle, it uses the left endpoint on the subinterval. And it uses the height of that left endpoint to put the rectangle. And then we have 5 rectangles. And then what is the approximation? 16.2. So that means if you calculate the area of each rectangle, we have 1, 2, 3, 4, 5, and then add them all together, you get 16.2. And what is the exact value of the area under curve? It's 18. So 16.2 is our approximation estimation for the exact value of 18. And you can also, by the way, you can also forget the applet and do this by hand, because this is so easy. It's also possible to do this approximation by hand. Another function that is good to work with is this one. Like, now update the applet for x squared plus 1. So we're gonna do x squared plus 1. Okay, it's gonna be a parabola. And then what? On the interval of 104, so the interval is the same. And then use the applet to compute. Okay, so this means left Riemann sum, midpoint Riemann sum, right Riemann sum, with 5 rectangles and 25 and 100, and then see what you see. Okay, so I'm gonna look at one of them. For example, left endpoint, left Riemann sum. And we want to see the effect of number of subdivision. For example, if you look at 5, look at 5. What do we have for 5? So for 5, look, this is the big picture. So for 5, if that means if we divide this interval, the interval of 104, into 5 sub-intervals, or in another words, if we do the estimation with 5 rectangles, then our approximation is 19.68. And the exact value of this area is 24. So with 19.68, we are approximating 24. So maybe I put this as a summary. So in this activity, with n equal 5 rectangles, we our approximation is the area approximation is what? 19.68. And what is the exact value of the area? This is given. We don't calculate this by hand. It is given that it's 24. Okay, so we are estimating 24 with 19. Now let's change it to 10. Now let's see what do we get if instead we use smaller rectangles and change this to 10 subintervals, or having 10 rectangles. So now we have the relative area to be 21.795. So now the approximation is what? Is 21.795. And we know that the real value of the area is 24. So do you see the difference? Look at the difference. When we use 5, the approximation is 19 for 24. When we use 10 rectangle, the approximation is 21. So now my approximation is closer to the real value of 24. So in other words, this is a better approximation. And finally, the textbook says, okay, try 5, try 25. Okay, I didn't try 25. So let's try 25. This is 25, you see? This is 25, which means that we divided the interval of 104 to 25 pieces. And then we put one rectangle on top of each piece, left Riemann sum. Now, what if we calculate the area of each rectangle and add them all together, then we get 23 point. Okay, so with n equal 25, our approximation for the area under the curve is what? Is 23.1072. 1072, which is of course it is a closer value to 24. So you see, we increase the number of rectangles, the number of subintervals, and then what we get is closer to the exact value. So we have a better approximation. And finally, the textbook says now try 100. So let's go by 100. So with n equal 100, which means that when we divide the interval into 100 pieces, let me see if we can do 100. Yes. Oh, it is so small. You see, it seems solid, but it's not. You see, there are 100 pieces here, 100 rectangles. You see that? We put, so this contains 100 rectangles. You see how teeny tiny they are? 100 rectangles between 1 and 4. And if the software calculates the area of each and add them all together, which is 23 point, it gives me an approximation of 23.77545, which is the so far is the best approximation of the 24, because look at the trend here. The trend is that look, with 5, that so this is the exact value, 24. Now what we get here is approximation, right? So with 5 we said the area is 19. With 10 boxes we said the area is 21. With 25 boxes, we observed that the approximation is 23. And with 100, we observed that the approximation is 23.775, which is pretty close to 24. So this is the better estimation of the real value. The real value is 24, and what we are doing is that we are doing estimation of the real value, right? But the observation here is that as we increase the number of rectangles, in another word, as we increase the number of subdivisions, then we end up with a better approximation. We end up with a value that is closer to the real value. So that's the idea. Look, you can do Riemann sum with any number of rectangles that you want, but the more, like 1, you can also use 1. And if you just use 1 rectangle, you get 6. And 6 is not a good approximation of the value of 24. But as you increase the number of rectangles, you will end up with a value that is closer to the real value, and it gives you a better approximation, better estimation. Okay, so that's the effect of n number of subdivision. So here we saw this part actually, that increasing, then we answered this question actually, increasing the number of subintervals positively affect the accuracy of the approximation generated by Riemann sum. The approximation becomes more accurate or closer to the real value. Okay, so you saw the idea, right? You saw that with Riemann sum, we get an approximation, but as we increase the number of subdivision, we get a better value. So recall that when we talk about increasing something, that's always like, let's go further. What about like, look, in this activity we just looked at 100, right? But what if we go to 1000, right? You will end up with a value that is closer to the 24. So this is going to give you a better value. So what about if we go further, like 10,000? Like with 10,000 rectangle, this gives me a value that is more closer to 24, and so on. So the idea is that, like, if you do 1 million, 1 billion, right? Then you will get a better estimation. So the idea is that we are looking for the area under the curve, right? and we are using Riemann sum. But the idea is that as we increase the number of, as we increase the number of subdivisions, the number of subdivisions, then we get a more and better estimation. Then we get a value that is closer. So what does this remind you? Look, what does it mean to get it, to get the n larger and larger and larger? That brings us the idea of limit, because limit talks about behavior of function at infinity. What does infinity mean? What does infinity mean? Infinity means very, very large value. That's a notation, but it means very large value. And the idea is that really for very large n value, well, you get a good approximation. So that's why we have the concept of limit. So when you take the Riemann sum, when you take the Riemann sum, so you know how to take the Riemann sum, right? When you take a Riemann sum, if you take a limit of that, and then let n to get larger. So notationally we say n goes to infinity, but what does it mean? It means, what does this mean to put n goes to infinity? It means that when you increase the value of n in this context, it means that when you increase the number of subdivisions, when you increase the number of rectangles, and here we are not talking about 5 and 10. When we say infinity, it's like about 1,000 and 1,000 rectangles and billions of rectangles and subdivision. So if you do that, then you get the you get the area of the you get a good value, accurate value for the area under the curve instead of approximation, because Riemann sum is just approximation, right? But when you take the limit, then that gives you the area under the curve. Okay, so uh, of course the function needs to be continuous so that it works, and then it doesn't, and then you know when the values are large, I mean when the n values are large, the number of boxes are large, then it doesn't really matter whether you do left Riemann sum or right Riemann sum or midpoint. The only thing that matter is that the number of, you see what I'm saying? So let me show you something. My point is that, like when you do 100 boxes, right, you get a good approximation. In this example, we did 100 rectangles and we end up with the estimation of 23.77545, which is a very close approximation of 24. Now, it doesn't matter whether you do a left Riemann sum or right Riemann sum. Look, in right Riemann sum, I also have a good approximation, 24.2020. Recall that, let me remind you something. When you do left Riemann sum, in this case, because the function is increasing, we underestimate it. When you do right Riemann sum, you overestimate it. But what matters is the error. How much is the error? For example, if you do a left Riemann sum, this is the error. Okay, the exact value is 24. Our estimation is 23.77545. Okay, 0.22. If you multiply it by 100, yeah, that's the error, right? And okay, 0.22 is the error when you do left Riemann sum. Now, let's see what is the error. What is the error when you do right Riemann sum? Okay, with right Riemann sum, the approximation is 24.22545. So we are overestimating when you do, in this case, when you do right Riemann sum, we are overestimating minus the actual value of 24.22. So you see, the error is the same. My point is that when the number of subdivisions are large enough, then it doesn't matter whether you do a left Riemann sum, right Riemann sum, midpoint Riemann sum, or any arbitrary value in between. No matter which one you do, the error that you get is so small, and that's a good approximation. Recall that none of them, when you deal with like n equal 100 or 50, none of them is the exact value. There is always an error, but it's what matters is that we are controlling that error by increasing the number of subintervals. We are making sure that error is small enough. Whether we are overestimating or are underestimating, it doesn't matter. What matters is that the error is small, and that makes the estimation a good estimation. So that's why whether you do left Riemann sum or right Riemann sum or midpoint Riemann sum, or you do any arbitrary value, which means that for the height of rectangles, pick any point in those subinterval, it doesn't matter. For any of them, if you take the limit of them when n goes to infinity, which means that if you evaluate that sum for very, 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 very large number of rectangles. We are not talking about 100,000. We are talking about billions and billions, very, very large rectangles. Then they are all gonna be the same. It doesn't matter whether it's left, right, midpoint, or any arbitrary value. They are all gonna give you the same value as the estimation of the area. Uh, and of course, if f is continuous and allow us to make the so in this way we are now ready to define integral, the finite integral. So in general, integral, and in this case, because we are doing over the interval, for example, we are doing this over the interval of 1 or 4, because we are doing this over, we are looking at the area under the curve over a specific interval. That's why it's called definite. And what is the definite integral of a continuous function on the interval? The notation, this is the notation that we use, and it's just the limit of the Riemann sum. That's it. So what you see here is just limit of Riemann sum. That's it. So for example, let's say here, right? If you do, if you see the integral of, for example, in this activity, if you see this notation, I'm going to first explain the notation. If you see the notation of integral of f of x, what is f of x in this question? X squared plus 1. Okay, so f of a, so this is the notation in general. So what does it mean? Here, this notation stands for integral. Imagine S. Now it's imagine we like expand that S. That S, because S, letter S is the beginning of sum, right? S can stands for sum, and we are doing sum, right? We are doing the summation of, we calculate the area of each rectangle and then we add all together. So this is sum, Riemann sum. That's why the notation of integral is like this. So integral has this notation. Why? Because integral is nothing other than limit of Riemann sum. So it's like a S that is like you stretch this S. That's about the notation. Okay. So this notation stands for integral. Here you put the function, and then here you put that respect to what variable, because sometimes you may have multiple variables. With respect to what variable you are doing this. For example, in this, in here, we are having this over x-axis. So we are doing respect to x variable. So we put d of x, and then here you put the interval. For example, you are doing this on the closed, you are looking at the area under the curve over the interval of a and b. So you put a and b. In this example, I'm gonna put the notation for this example. What is the function? Is x squared plus 1. So we are doing the integral of x squared plus 1 respect to x from 1 to 4, right? And what is this? It's nothing other than limit of Riemann sum. It's limit of Riemann sum when n goes to infinity. What is n? It's the number of subintervals, number of rectangles. So that means you take the Riemann sum of this function, this Riemann sum of x squared plus 1 over the interval of 1 over 4, and then increase the number of n. That's the integral. That is what we called, and it's called definite because we are doing it over a closed interval, which is in this example 1, 2, 4. And if you want to know what is this notation, I can explain. This is a Riemann sum. I can remind you what is this notation. So we are taking the limit of Riemann sum. What is Riemann sum? It's a summation. So sigma stands for summation. Summation of what? The area of rectangles, right? Recall that. Suppose you have these rectangles, right? So what is Riemann sum? We add the area of each rectangle. So what is the area of rectangle? Height times width. So for height, it doesn't matter. You can use left, right, arbitrary because n is large. So I'm going to put f of x I. And in your textbook, it puts the notation a star to show that this can be any. X star means any point on that interval. Means that, for example, you're doing over this rectangle, pick any point here. Xi. So it doesn't matter which point you pick. Pick any point and then evaluate the f of that point. That gives you the height. So this is going to give you the height of rectangle. This is going to be the height of rectangle because we are doing area, height times width. And what is width? Width is delta x. What is delta x? Remember, delta x is that we divide the subinterval. What is the interval? In this case is 1 to 4, right? 4 minus 1 divided by n, the number of rectangles. In general, b minus a divided by n, which means that we divide the interval into n pieces, n equal size pieces. The size of each piece is delta x, and that's gonna be the width of rectangle. So height times width gives us the area. So we calculate the area of rectangle, and it's the indices are how many rectangles do we have? We have 1 to n. Like this, let's say, I think your textbook starts from 1 or 0. No, it starts from 1 to n. We have n rectangle. This is the first rectangle, the second one, the third one, up to we have n rectangle. So we have to calculate the area of each rectangle. So when you put 1, it goes and calculate the area of the first rectangle. When you do 2, it goes and calculate the area of second rectangle, and so on. And what does sigma mean? Sigma means it adds all together. So that's just Riemann sum. And then n goes to infinity. That gives you the integral. Okay. So what is integral? It's nothing other than limit of Riemann sum. That's it. Now, what do you want to put here? You can put either left Riemann sum, right Riemann sum, midpoint Riemann sum, or arbitrary value. Like pick any arbitrary value, calculate f of that value, that gives you the height of rectangle, multiplied by delta x, that gives you the area of rectangle, and repeat this for the all n rectangles and add all together. That's it. That's the Riemann sum. And then take the limit. So we call this symbol the integral sign. Values of a and b are called limits of integration, and the function f called integrand. In this case, the integrand is x squared plus 1. So these are just some name you need to know. And then the process, this process of determining the real number of this integral is called evaluating the definite integral. Yes, there are so many interpretation of the integral, but for now, we just focus on the meaning of area. So yes, you can you know, there are many ways that you can interpret the meaning of integral. But now we look at this as a measurement, that this measures the net signed area bounded by the function and x-axis on the interval of a and b. So in a case like this picture, right? Look at this picture. I'm gonna just denote this using integral notation, right? This is area under curve. right? This is area under the curve. We said that area under curve can be represented by integral. So let's practice that. So this is gonna be the A1 is gonna be the integral of f of x d of x from a to b. Maybe I do. Let me see if I can paste it here. No, wait. Let me see. Mm, okay, I think I have to take a screenshot. Yeah, no, it worked. Okay, so this one, A1, oh, the coloring is not good, but I try to explain that here and then I can explain it. So A1 is the integral of f of x. So this is A1, the respect to x from here to here, which is, I cannot see it here, which is a to b. This is a, this is b. So this is the integral. So A1 is the integral of f of x respect to x from a to b. A2 is the integral. A2 is the integral of f of x d of x from b to, what's that number? C. This is C. And this is D. So finally, A3 is in fact the integral of the function respect to x from C to D. So you can represent these areas using your integral. And now if you were to, I mean, suppose you know the value for A1 and A3, right? Suppose you know the value for A1 and A3. And if the question asks you, what is the, let's say, what is the integral of f of x, d of x from a to d, this is a to d. Look, this is a to d, the whole highlighted area. Then, because you know that this is gonna be the area under the curve. So it's gonna be A1 because A1 and is above x-axis, so come as positive. A2 is under x-axis, so that's negative, and then plus A3. So it's like we add the value of A1 and A3, and then we subtract A2 because that's a negative one. Okay. And in a case like this, this is easy to evaluate because we know how to calculate this. Look, so for example, here f of x is 2x plus 1. And the question is, what is the integral of 2x plus 1? Maybe let me copy image and then show it to you here. Look, the question is this, right? The question is, what is the integral of 2x plus 1? The question is, what is the integral of this function 2x plus 1 respect to x from 1 to 4? So this is gonna be the area under the graph within toward, I mean, the area that is between the graph and x-axis from 1 to 4. By the way, this is in the picture, this is 1 and this is 4, right? So, I mean, from geometry, we can calculate this area. This is not difficult to calculate this from geometry. And you can do that and you will see this is gonna be 18. It's half of 3 plus, because this is 3, this side is 3, this side is 9, and this side is also 3. So we add the value of these two sides, 3 plus 9, and then we multiply it by the height. which is 3, and then we divide it by 2. So we get 18. So you see, you evaluated this integral just by using the fact that this area, this definite, definite integral is the same as the area under this graph, which happens to be in a shape that we know how to calculate the area. For example, in this activity, it says use known geometric formula and the net side area interpretation of the definite integral to evaluate each definite integral. So I'm going to show you one of them, and then you can do the rest. For example, 3x from 0 to 1. Okay, let's do this. So the question is, they evaluate this. So this is the activity. The question is evaluate the integral of 3x respect to x from 0 to 1. So, I mean, we need to use geometry. So far, we know that this is the same. This is the question. So far, we know that this is the same as area between the graph of 3x and x-axis between from 0 to 1. So let's draw it. Let's draw it and see if we can calculate this area by hand. 3x. So this is x-axis, y-axis, 3x. You know, if we have 2 points of it, we can draw it. At 0 is 0. I'm trying to draw 3x. At 0 is 0. At 1, it's 3. Maybe I make it bigger. At 1, it's 3. 1, 2, 3. Right? Then we connect it. So this line is the graph of 3x. Now this integral is the area under the curve and x-axis between 0 and 1. So it's going to be this part. Look. This represents this area. Okay, this area. So we need to calculate this area, but pay attention that this is a triangle, right? This is a triangle, and we know how to calculate the area of triangle. And actually, this is a right triangle. But anyway, to calculate the area of this triangle, I need to know what is the so we need to calculate this area. But because it is a triangle, it's half of height. What is height? Height is 3 times base. Base is 1. So it's going to be 3 over 2 or 1.5. That's it. So we use geometry to evaluate this area, but we know that that is the same as this integral. So this integral is 1.5. So I recommend you guys to do BCD. You should be able, I mean, you can use geometry to calculate those areas. This is a good way for you to see the connection. Okay, now let's look at some of the properties of the finite integral. Look, the first property is pretty trivial. If you look, what does this mean from geometric perspective? If you take an integral of a function from a point to itself, right? So what does this mean? Look at this in terms of geometry: x-axis, y-axis, and then you have a curve for f of x, the graph of f of x. And suppose this is point A. So what does this mean? It's the area between the graph and x-axis from A to A. Okay, so that's gonna be just this straight line, right? So there is no area. And my point is that there is no region when you're a starting point and ending point are the same, no region, no space is created. So there is no, when there is no region, there is no area. So this is gonna be 0. So the area is 0. Since the area is 0, therefore the integral is also 0. Okay, so the first property is that if you take a definite and the definite, if is continuous function and a is a real number, then this definite integral, which is from a to a, which means any point to itself is 0. Another property that is very easy to see geometrically is that if you divide an interval into two subintervals, like let's say, for example, look at here, you have the interval of A and C, and then you break it into two subintervals, like A to B and then B to C. Then you see that in terms of area, the area, you can say the area from A to C, or you can say the area from A to B, which is A1, plus the area from B to C. That gives us this property, the second property, that because the area, the entire area is A1 plus A2, for that reason, the integral from A to C is the same as the integral from A to B and then B to C. And finally, if we have this property that if you switch the place of these two limits of integral A and B, then you get the negative sign. So maybe I write this two property here to summarize it. So suppose this is A, B, C. Okay, so the integral from A to C of a function is the same as taking the integral from A to B and then add the integral of f from B to C. And the last property was that if you take the integral of A to B, if you take the integral of A, oh my God, what happened? I lost my whiteboard. So the last one says integral of B to A is the same as A to B, but with a opposite sign. Okay. Let's see what else. We have more properties, like the properties for a derivative. Do you remember for derivative, if you multiply it by if you multiply the function by a constant, you just and then take the derivative, then you just carry out that constant, that multiplier with the derivative. And then the sum rule, you're taking the derivative of a sum, it's the summation of these individual derivatives. We have the same property for integral. If a function is multiplied by a number, you can just you can just carry that multiplier and then take the integral of f. And also, if you're taking the integral of a sum, it's the same as taking the integral of each individual and then add all together. So these are the similar property that we had in for derivative. Okay. For example, look at this activity. It says, suppose the following information is known about function f, g, x squared, and x cubed. Okay. Use the provided information. So this information is provided, and then use the provided information and the rules in order to process this evaluation, this integral evaluation. Okay, let's do the first one, A. So in this activity, So in this activity, we are doing part A, which says take the integral of um, part A, integral of f of x, b of x from 5 to 2. That's the question. What information is given? We know the integral of f from 2 to 5, which is 2. So since this is the opposite, so it's going to be the same value but with negative. So in other words, this is going to be integral of f of x dx from 2 to 5 but with negative sign. So it's going to be negative. What is the value of integral from 2 to 5? It's 2. So it's going to be negative 2. Maybe I do one more. Part B. What does it say? Part B says an integral of g from 0 to 5. So part B says what is the integral of g function g from 0 to 5, right? That's the question. Okay, what information do I have? I have for function g, I have the integral from 0 to 2, and then I have 2 to 5. Oh, okay. I don't have it from 0 to 5, but I have it on the pieces from 0 to 2 and then 2 to 5. So we can use the property that this is the same as integral of function g from 0 to 2 plus the integral of the same function from 2 to 5. Okay, so now because I have the value of each one, so we can substitute that. From 0 to 2 is 4, so that is 4. And then from 2 to 5 is negative 1. So this is going to give me 3. And then, and part C says that take the integral of the summation of f and g from 0 to 5. Okay. So part C, take the integral of f, this is the function f plus g respect to x from 0 to 5. That's a question. Okay, let's see. We just evaluated the integral of g from 0 to 5. So we know the property that this is the same as the integral of f. It's a summation. This is the sum rule, right? So we can take the derivative of f from 0 to 5, and no, sorry, not the derivative, the integral, and then add it to the integral of g from 0 to 5. So over the same interval, and then let's see, what is the integral of f? F from 0 to 5. Okay. F 0 to 5. Okay. So I don't have F from 0 to 5, but I have it from 0 to 2 and then 2 to 5. So I'm going to replace this. Look. So this is the integral from 0 to 2. We can write it as in two pieces, from 0 to 2 and then from 2 to 5. Okay. And then plus the integral of g. For g, we already know what is it. Okay, now let's substitute that. From 0 to, for f from 0 to 2, f 0 to 2 is negative 3. Okay, so this is gonna be negative 3 plus. And then 2 to 5 is 2. And then the last one, g from 0 to 5, we just evaluated that in the last part. The integral of g from 0 to 5 is 3. So now you can simplify it. This and this cancels, so the answer is 2. Okay, so this is just like playing with the properties, different properties. So I'm going to leave the rest for you. I did part A, part B, part C. I'm going to leave part D and E for you. Just use the information given on top, use the properties that we learned. This is the sum rule, this is the constant multiplier rule, and and this is when you change the limits. It's like I just use this rule and use the information given to practice this. So I think that's good for now. Yeah, I think that would be enough for this section. As long as you, I think the main takeaway from this video is that the definition of integral, which is nothing other than the Riemann sum. We learned Riemann sum in previous video, and here we just take the limit of Riemann sum, and we are taking the limit respect to n. N is the number of subdivision, number of rectangles, and we saw that if we take the limit, which means that if we increase the number of subdivisions for very large value, then this Riemann sum gives us a very good approximation of the area, and we define the integral from here. So now I encourage you to do the exercises of this section. Thank you for watching this video. I'll see you in the next one.